Okay, so this is the feedback video for the 2018 geochemistry exam. Just for the stable isotope questions. So this is questions 1 and 3. Question 3 will actually be in a separate video because these videos are getting quite long, so I ramble on, give lots of useful detail and feedback and that kind of thing. So there'll be another video which you should look for somewhere, or learn, or on YouTube, or however the internet works these days, for the if you've done that question. So this will be the one about silicon isotopes, and the other one will be about oxygen isotopes. But anyway, let's move on. So I'm just going to include me up here in the corner so you can look at me while I tell you stuff. So just some generic advice. I guess this is in all of the feedback videos now, so don't just rely on previous exam questions because occasionally they do change. It's a good idea. I gave some examples in one of the tutorials of how we can kind of read into these exam questions, comprehend what they actually mean, and maybe come up with our own questions to try and help revision. Looking at each part of the course and going, what is this trying to? What is the content of this bit of the course? What are we trying to get across? And what kind of questions might we ask? And then you can use the discussion forums and talking to each other, and maybe even talking to me about this kind of thing. We could maybe discuss it, which would be fun. Moving on. Yeah, stay relevant to the question, that kind of stuff. Don't write just random stuff about that subject area. Be specific to the question. But actually, once you've answered the specifics of the question, it is good to kind of like start to fill out your answer with some extra details, or maybe opposing kind of counter examples, which might be useful to get you the super high bonus points. So these are the mark distribution for my my questions. So question 1, which was about silicon isotopes, which is this video, which was actually answered not that well. So there are quite a few things that people missed out on, some of the really easy marks in the early part of the question, which was a bit disappointing. But the other question, people had a range of different answers, which got a range of different marks. You'll be able to see where you are in the exam feedback session. Please come to the exam feedback session, and we can go through what you did and what I wanted. But you should also watch this video because it will also tell you what I wanted, but not what you did. You might remember that. So I kind of say this every year. You should always start revising earlier. Actually, the data that I have from, sorry, gratuitous air quotes there. The data that I have from seeing when you were watching some of the videos actually showed that you were consistently watching them throughout the, well, at least somebody was watching them. Somebody in the UK was watching some of the videos related to the course throughout the course. Obviously a big spike right before the exam. But yeah, so do work throughout the course. Otherwise, revise at the end is a mug's game. Right, so getting on to the first question. So there was quite a lot of description before the question for real started, and really the bulk of this question was really about this graph here on the right. So let's just read through the description of the graph as given it. So basically looking at a situation in the surface ocean where the element silicon is added from mixing of deep waters. So basically what we're doing is we're starting out with an influx of dissolved silicon into the surface ocean, okay, at the beginning of the year, okay, in winter. And then throughout the year, in spring and summer, the nutrients progressively gets used up. So you can think of maybe sketching out maybe the concentration of nutrient through time. We start out with lots, okay, and then through the year, we gradually deplete the surface ocean, kind of, so the concentration goes down through time. Okay, so the figure doesn't show that change in concentration. The figure shows the change in isotopes, but we'll go over what this is. The figure shows the idealized change in silicon isotopes as silicon isotopes is removed from the surface ocean and buried in the sediment by sinking diatoms. Okay, so the first part of the question is really asking you to to identify which parts of the diagram mean what. So we'll just look at, and you can see that these questions are not actually, giving you huge amounts of marks, but there are places where quite a lot of you lost out on perhaps some easier marks, which just went because you got these questions wrong. So let's just start out looking at the first part A. So of the points X, Y, Z, so these are the, have I got the right pointer over here? Yeah, so we've got X, Y, and Z. Which of them is the silicon that's brought up into the surface ocean? So this is the dissolved silicon that's brought into the surface ocean at the beginning of the year. So the things to look at here are, first of all, start looking at the horizontal axis at the bottom. So this is the fraction of silicon remaining. So this is none of it remaining. So this can't be the amount of silicon at the beginning, because it's when it's all gone. So our initial amount of silicon is all of the silicon remaining, which is the beginning when it first upwells. So that means that our answer must be Y or X. If you think about what the isotope composition of the bulk, all of this silicon that's brought to the surface ocean, if at the end of the experiment or the end of the situation, all of that silicon is removed and put into sediments, that bulk sediment must have the same silicon isotope composition that we started with. And that is this point here. So that means that the only 2 points that have got the same, it's working, no, not doing, the only 2 points that have got the same isotope value are Z and Y, which means that Y has to be the silicon that's brought to the ocean surface at the beginning of the experiment. Okay, so you might have just known that from like knowing these diagrams and understanding where this is the starting composition, and then through time the dissolved phase evolves up this path, and the initial product, so that the diatoms that are forming from that will be offset from that, but then we'll follow them up at a constant fractionation factor offset, and then you're accumulating these, and if you kind of sum up all of these, you end up with kind of this curve, which ultimately ends in your starting composition. Okay, so Y was the answer for A. So the next question is basically, of the lines A, B, C, and D, which ones represent the evolution of the dissolved silicon, the accumulated sediments, and the diatoms growing in the surface ocean? So the first thing to pick out here, there are 4 lines, and there are 3 things to assign them to, so we need to pick out the one that's wrong, and that is C. So C is the bulk mixture. So if we take all of the silicon in the whole system, that should always be the same composition. It doesn't matter what form it is. If we add up all of the silicon that's in the dissolve phase and all in the solids that have accumulated in the sediment and that are in the water column in diatoms, if we add them all together, there's no way of losing silicon from that kind of total sum. So that must have the same isotope composition through all of the time where we're transferring silicon from the dissolve phase to the diatom phase. So this line from Y to Z, that's the bulk mixture. So we think about what the next things are. We look at the dissolved silicon, so that's line A, and if you'd have got Y right, that's the only of the other lines that goes through Y, so that must be dissolved silicon. If you didn't get Y right, then it makes getting that one a little bit more difficult. So the diatoms, the accumulated sediments, so the accumulated sediments, if we accumulate all of the silicon that we started with, that must have the same composition. If that all the silicon water gets put into the sediments, it must have the same isotope composition because we've not lost any silicon anywhere. So the only other line that goes through that one is this dotted line here. So that must be the accumulated sediments line, which leaves B being the diatoms that are growing in the water column. This is basically the instantaneous product from the dissolved silicon. So that's line B. Okay, so that's there. So if you got those right, that's an easy kind of like 20% of the whole marks in the bag. If you didn't get it right, then marks lost. So I guess a little bit of you win some, you lose some there. Right, so the next part of the question was actually universally poorly answered, because this was one which we could actually come up with a number for the fractionation factor, and very few people actually managed to do this. Quite a few people got it kind of completely wrong. So there are some things which you would have needed from the practical, some from the lectures to address this. So the question is asking you to estimate the fractionation factor between the dissolved silicon and the diatoms. So first of all, you would need to have identified the right lines in this graph. You need to identify that dissolved silicon follows this trajectory, and the diatoms that are growing from that at any kind of one time, we've got some fraction of at any one time we've got some fraction of silicon remaining. We'll have dissolved silicon of this composition off there and diatoms of this composition. And the important thing is that at any kind of one time, the distance or the vertical offset of these two lines is always the same. Okay, this is the fractionation between them. Okay. So from this difference in the isotope ratio expressed in this delta notation, can we work out what the fractionation factor is? So before we go in and actually do that, I think some of you made some assumptions about what the fractionation factor should be. And this is good, right? So this is the kind of thing you should do before you try and do some calculations. You know, what are you expecting to get? And I think I gave you some credit for making kind of sensible statements about things like it should be close to 1. It should be just less than 1. Okay, these are things that we could assume, and we could check that our answer actually comes close to those. Now, we think that the fractionation factor should be close to 1 because isotope fractionations are generally small. Now, why should it be less than 1? Well, if we look at, there are two kind of arguments that we could make, because the first argument we can make is that the fractionation between kind of an inorganic phase and something that biology produces from that, okay, so that process will quite often favor the incorporation of the light isotopes into the biological material. Okay, so you could say, well, I'm expecting there to be lighter isotopes in the diatoms, therefore the fractionation factor, so should be of diatoms to dissolved silicon, should be less than 1. We could also look at the graph, the diagram here, and see that the dissolved silica is always isotopically heavier than the diatoms. So the diatoms are isotopically lighter, so we therefore expect the fractionation factor to reflect that being less than 1. Now, if you got that the wrong way round because you set up your fractionation factor the other way round, then that's okay. I mean, the question does define which way round the fractionation should be. It should be the ratio in the diatoms divided by the ratio in the dissolved silicon. But nonetheless, you would have got some credit for thinking along the right lines. So this is the thing that we want to know. We want to know the fractionation factor between the diatoms and the dissolved silicon, and we can define that by the ratio in the diatoms divided by the ratio of the dissolved. Now, that's the absolute isotopic ratio. We don't have that. We only have the isotopic ratio expressed in the per mil notation. So we need to get to that somewhere. So first of all, let's just estimate that number from the graph. So we could use any of these pink lines anywhere. So I'm going to use the one at the start, but you could use the one over here. So we're looking at the difference between the diatom minus the dissolved silicon. So you could use kind of maybe 3 minus 4, or this is 0 minus 1. I think I go through what's the difference of the large delta, capital delta diatom minus dissolved is the difference in the two delta notation isotope ratios. Okay, so that gives us a delta value of minus 1. Okay, now hopefully you'll have remembered from the practical and also from the lecture, but mostly from the practical, that there is this relationship between the delta value and the fractionation factor, and this is it. So the delta value, the difference between two isotope ratios expressed in the per mil notation, so this thing that we've just worked out to be minus 1, that's equal to 1,000 times log alpha, or approximately equal to 1,000 times alpha minus 1. Doesn't matter which one you use. So all you need to do is substitute in your value that you got from reading off the graph, and then rearrange those equations, or rearrange one of the equations. They give the same answer. So there's how you rearrange them. Feel free to stop the video now and work through those rearrangings if you can't do it, but you should be able to do it. And you get an answer of 0.999. Okay, and that is the fractionation factor. It's not 0.99999 recurring, it's 0.999 because the delta value is -1. Okay, so that's the answer. Okay, you got a bunch of marks for getting that answer. Perhaps I was a little bit stingy only giving 10 marks for it, but I guess it does mean that if you couldn't do any of that, you only lost 10 marks at a maximum. Maybe you got some more for getting part of it. But anyway, here we go. That's what you should have done. So there you go. Right, so moving on to the last part of the question. So this is where kind of the bulk of the marks are given out. So the first question, silicon is present in these phases: dissolved orthosilicic acid, which is the formula there, and diatoms. Nice picture of a diatom over here on the right. So that's not really a question, that first sentence. The next sentence is really we're really asking for is explain the mechanisms that cause isotope fractionation between the two forms of silicon in the ocean. So that's how do we get isotope fraction between diatom opal and the silicic acid dissolved. And then the last was a bit of a kind of I guess non-intuitive kind of question. You had to really think about this one in terms of answering it. So can silicon isotopes be used as a temperature proxy? So because we don't really use it as a temperature proxy, but could we? So we'll come on to that one in a bit, but let's just focus on part D first. So really another way of writing that question, okay, why do isotopes fractionate between silicic acid dissolved and hydrated silicon? Now, I guess hopefully most of you can remember that there are two ways that isotopes really can fractionate. They can be either equilibrium fractionation and kinetic fractionation. Now, I think quite a lot of you wrote about kinetic fraction. Sorry, some of you wrote about kinetic fractionation. Quite a lot of you wrote about why isotopes fractionate under equilibrium conditions. Now, there were some quite good answers there for why equilibrium isotope fractionation works, but because this formation of these diatoms is a biological process, most of the fractionation is probably kinetic isotope fractionation. So that's what I was really looking for. I think I gave quite a lot of credit for people who wrote about equilibrium fractionation and wrote correct stuff in that answer. But what we're really looking for is a description of why we get kinetic isotope fractionation. So I'll go through that now. But if you'd have written about just equilibrium isotope fractionation, you would have got credit for that. You would have got some marks, but not, the mega bucks that you would have got for getting what I was exactly looking for. But still, you wrote correct stuff, and there may well be equilibrium processes that go on in the formation of these diatoms. So good for you. Okay, so for kinetic isotope fractionation, I guess the first kind of point that should be kind of like made in any kind of description is that if you have any kind of chemical bond, a identical bond with heavier isotopes should be stronger. Okay, and you could make that statement. You could get some more credit by explaining why that is in terms of the vibrational frequency and these kind of energy wells and being in a more stable state when you get kind of like right down into the bottom of this energy well. Now, that's good. It doesn't explain why we get isotope fractionation for the kinetic case. It just tells us that the bonds are stronger. So the next thing is to say, well, actually, why does the bond strength matter? And it matters because the bond strength has an impact on the activation energy of any kind of chemical reaction. So the stronger the bonds are, the harder they are to break, the higher the activation energy, which means that any chemical reaction will go slower because it has a higher activation energy. And that's this Arrhenius relationship here. So it'd be really great if you kind of included that equation in your answer to explain that the reaction rates will be dependent on activation energy, which is then dependent on the isotope ratio. So heavier isotopes, slower reaction rates. And then you need to go on and say things about, if we have slower reaction rates, then if the reactions don't go to completion, if we kind of don't take all of the silicon from the ocean every time we make a diatom, which we don't. Each diatom only takes a tiny amount of silicon out of the ocean. It means that the diatom formation will preferentially favor those isotopes which can react faster. So that will be the lighter isotopes. There may also be processes going on in the diatom as it's growing which involve diffusion. Okay, so any reaction that involves diffusion will also favor products being enriched in the lighter isotopes because they can move faster. So a little bit of a description of that and the kind of equations of motion, I guess, the kinetic energy relations to motion would also be useful to have in there. So those are the kind of explanations we're looking for in terms of why we get kinetic isotope fractionation. So you could have given a quite simple answer for that for fewer marks, and if you'd have added in some of these details about why we get stronger isotopes why stronger bonds are formed by heavier isotopes, then that would have been better. You could have more marks. Right. So moving on now to this last part. So this is, can the isotope ratio marine diatoms be used as a temperature proxy? Why or why not? So I guess we can maybe rewrite this in a different way. So is the isotope fractionation in any way temperature dependent? Okay. And if it is there a reason why we couldn't make use of that as a temperature proxy? Okay. So usually when we think about temperature proxies and oxygen isotopes, we're looking at things maybe like oxygen isotopes. We'll see that maybe in the other question. But would silicon isotopes be temperature dependent? And then the critical part is, but even if they are temperature dependent, is there something else going to ruin it for us? So let's have a think. Okay, so going to the parts of the lectures on the temperature dependence of isotope fractionation, we can see that if we have, in the case of an equilibrium isotope exchange, then there should be some, if there is an isotope fractionation, then that will be driven by some kind of free energy. And if there's a free energy driving that, then we'll have some component will be enthalpy, and some will be entropy, will be kind of driving that, which means that the entropy term has a temperature dependence on it. So under equilibrium conditions, there should be a temperature dependence to the isotope fractionation. Okay? Now, what that means in terms of this diagram is that the fractionation factor alpha will change, which will then change the delta, big delta, which is the difference between the dissolved silicon and the diatoms that are growing from that. So that's effectively changing the length of this line here. So at lower temperatures, we might get a slightly larger fractionation. This line might be a bit longer. Okay? And that might impact our ability to use it as a temperature proxy. I mean, if that changes, that'll change the isotope ratios that we're measuring in the sediments, certainly. So maybe we're a go. It's an isotope temperature proxy extravaganza. Now, that assumes that the isotopes are being incorporated into the diatoms under equilibrium conditions. Now, that's probably not the case. So is there a temperature dependence to kinetic isotope fractionation? So actually, yes, there is. Now, this is some maths which wasn't in the lectures, but you, I guess, you could have quite easily kind of derived it. But yes, temperature is a control on the amount of isotope fractionation you get under kinetic fractionation. So a way of thinking about the fractionation factor under kinetic conditions is the ratio of the rate constants. So I've made a mistake here. This should be heavy over light. What an idiot! Hey. But anyway, I've got there we go. This should be heavy over light, but hey ho. I've even managed to get it correct here when I put it in. But anyway. So the fractionation factor is the basically ratio of the reaction rates of the heavy and the light isotopes. So we can write that out in terms of, we can substitute in this Arrhenius equation, okay, into here, and we can see that these are dependent on the activation energies. Okay, so this term here is going to be bigger. It's going to make this whole thing slower because it's a negative exponent. So the key question when thinking about rearranging this is this temperature term going to cancel out? And no, it doesn't. Okay, so when you rearrange it, you actually find a relationship between alpha and temperature. So yes, kinetic isotope fractionation is temperature dependent, and you could have gone through that and said, yep. And actually, I gave marks for the equilibrium case and not, explaining that actually, yes, silicon isotope fractionation is or should be temperature dependent. Now, unfortunately, for those wanting to use silicon isotopes as a temperature proxy, it's not quite that simple. Okay, so we need to answer this last part of the question. If it is temperature sensitive, which it is, can we use it as a proxy? And kind of no, we can't. So just like with oxygen isotope, one of the problems with using isotopes as a temperature proxy is that we need to have both phases which are in equilibrium, or at least which have fractionated. Okay, so in the case of using carbon isotopes, using oxygen isotopes in carbonate, calcium carbonate, we need to have the water and the calcium carbonate. If we don't know the compositions of both of those, we can't work out what the fractionation factor was, therefore we can't calculate temperature. And it's exactly the same with silicon isotopes. So the length of these lines may be, in fact, is dependent on temperature. So when we have higher temperatures, these lines will be shorter. So if we could measure the diatoms, we still couldn't work out temperature because we would need a measurement of the ocean water, silicon isotopes, which is not preserved in the geological record. Additionally, so that would be an important thing for you to say in can you use this as a temperature proxy? No, because we need to know, or we need to at least make some assumption about the composition of the other phase. The other thing that's a problem is that if we look at diatoms in marine sediments, actually what we tend to measure is the accumulated sediments. Okay, because if we're picking the diatoms out of the water column, kind of one by one, then why don't we just measure the temperature of the water that we're picking them out of? So if we're looking at the geological record, it's actually measurements from down here we'd be measuring. And these, again, there will be some effect of temperature on kind of the shape of this curve, and because the shape of this curve is dependent on the length of these lines. But the biggest control, and actually what isotope ratio you might measure in the sediment, is how far you've moved along this line. So what the fraction of silicon that has been actually removed from the surface ocean is. So if you're in an area where you're taking all of the silicon out of the ocean in the all of the silicon that makes it in the surface ocean, that gets taken and scavenged out to the bottom, you'll end up with this isotope composition. And that will just be the composition of the bulk silicon. So that won't be temperature dependent. And if you're back here somewhere, the isotope ratio that you get will, if you've maybe used up 80% here of the silicon in the ocean, then the problem might be that, well, the problem would be that the isotope ratio that you measure at this point here will be dependent on temperature, which is great, but you don't know whether you've used 80% or 70% or 90%, and that is a bigger control on the isotope value that you measure than the change in temperature. So the amount kind of effect will be greater than any isotope ratio change due to temperature. So that's the main thing we're looking for in the answer here. The first of all is that we don't have the other end member, not the end member, we don't have the other kind of phase, we don't have the dissolved silicon to actually measure the fractionation factor, and the isotope ratio preserved in marine sediments will be largely dependent on how much silicon has been used in the surface ocean rather than the temperature at which it formed. So those are the two things we're looking for. You could also add things like worrying about all of the other things you have to worry about generally for paleogeometry proxies. Is it diagenesis? Is there a, something like that? So those are things you could have had. So this is the end. This is the end. Hopefully this has been enlightening. You've learned some stuff about question 1 and stabilized fractionation and Rayleigh distillation, which was the graphy thing, which you should have. Yep. So, yeah, there you go. Just stop now. So, yeah.